Hello, grade 10s. In today's lesson, we are starting the topic of electricity and magnetism. And this topic only consists of two sections. The first one is electrostatics, which we will be starting now, and the second one is electric circuits. Let's take a look at our objectives. We're going to understand that all materials are made up of positively charged protons and negatively charged electrons. We will describe an object as neutral when it has the same number of positively charged protons as the number of negatively charged electrons. Protons and electrons have the same size charge on them, but in the case of a proton, it is positive, and in the case of an electron, it is negative. So a proton and an electron will have charges that will cancel each other out. We will describe positively charged objects as objects that are electron deficient. That means that they are lacking in electrons. And negatively charged objects are objects that have an excess of electrons. So that means that they have extra electrons on them. Protons cannot move around. It is only electrons that can move, which is why for an object to be positively charged, it is missing electrons, and for an object to be negatively charged, it has extra electrons. We will describe how objects can be charged by rubbing, and will understand tribo-electric charging. We will state that like charges repel and opposite charges attract. We will also state the principle of conservation of charge. We will apply the principle of conservation of charge using this formula, where the charge on each sphere is equal to the sum of the charges on two spheres divided by 2 when they come into contact with each other and then they separate. We will state the principle of charge quantization, and we'll apply this principle based on this formula. Now, what charge quantization means is that every electron has a specific charge associated with it, and every proton has that same charge associated with it, except that it's positive instead of negative. But any charged object has to have a charge that is a multiple of the charge of one electron or the charge of one proton, and that's because we don't get a piece of an electron. We don't get a third of an electron or half a proton. They come in whole electrons and in whole protons. So the total charge on an object, let's say if it's negatively charged, can be calculated as the number of excess electrons on that object multiplied by the charge of one electron. And lastly, we are going to understand the process of polarization, which will explain to us how charged objects can also attract uncharged objects. So remember that opposite charges attract and like charges repel. But if we have a charged and an uncharged object, they also attract due to the process of polarization. Let's talk about balance of charge. Electrostatics is the study of electric charge, which is static or at rest or not moving. The moment electric charge, like electrons, are moving, they are creating electrical energy or electricity. But here we're dealing with charges that are at rest. Now, obviously, all objects contain a lot of electric charge because if you think about your body, it is made up of trillions of atoms, and each atom contains positively charged protons and negatively charged electrons. So, an object like your body contains a large amount of electric charge. if you have the same number of electrons as protons, then the net charge is 0. The object is electrically neutral because one proton cancels out the charge of one electron. If there's more of one type of charge than the other on the object, then the object is said to be electrically charged. So let's say that your body is made up of 1,000,000,000,000 protons and 1,000,000,000,000 electrons. That makes your body neutral. It is electrically neutral. But if I add some electrons to your neutral body, now your body becomes electrically charged. And it becomes negatively electrically charged because we have added a negative charge in the form of electrons to your body. We can therefore calculate the total charge on you based on the extra electrons that are on your body. But remember that those other 1,000,000,000,000 electrons and protons have cancelled each other out. So when we look at the charge of an object, we are only looking at the charge that is in excess or in deficit. We're not looking at all the electrons and protons on the object that are cancelling each other out. As I already mentioned, protons don't move around. They are tightly bound in the nucleus of an atom. So the number of protons in an object can't change. If you have 1,000,000,000,000 protons in your body, that can't change. However, electrons can move around. So if you have 1,000,000,000 protons and 1,000,000,000 electrons that make up your body, then you are electrically neutral. If you have gained electrons, you become negatively charged by that amount of electrons that you've gained. And if your body has lost electrons, then you become positively charged based on the number of electrons that your body has lost. So a negatively charged object has an excess of electrons. It has extra electrons on it. And a positively charged object has a deficiency of electrons, meaning that it is missing a number of electrons relative to the number of protons in that object. So if we look at this diagram here, we have 6 positive charges and 6 negative charges. So plus 6 minus 6 is equal to 0, which gives us a neutral object with a net charge of 0. Now remember that the number of positives can't change. So in all 3 diagrams, we have 6 positive charges or 6 protons. But in this diagram here, we have removed 2 of the electrons. So now we have more protons relative to the number of electrons, which means that we have a positive charge. The net charge is plus 2. And over here, we have extra electrons relative to the number of protons. So if we have 6 pluses and 9 minuses, then the net charge is minus 3. It is a negatively charged object. Now we need to talk about tribo-electric charging and the law of charge conservation. Objects can become charged by contact or with being rubbed with another object, which means that through the rubbing process, these objects can gain or lose negative charge, meaning that they can gain or lose electrons. Now, not all objects have the potential to gain or lose electrons. So, for example, charging happens when you rub your feet against the carpet. That means that as your body walks against the carpet, and that depends on the material that your shoes or socks are made of, and it also depends on the material that the carpet's made of, then what will happen is electrons from the carpet are going to hop onto your body. Now, that means that your body becomes negatively charged because it has excess electrons on it. And so when you touch another person or when you touch a metallic door handle, you'll feel a shock because that excess charge that you've gained from the carpet is discharged, possibly through your finger or through your hand if you're touching another person or a metallic handle with your finger or with your hand. Now, I'm going to make a comment here that I'm going to come back to a little bit later, but what I want you to realize is that you and other people, as well as metallic objects, are electrical conductors. And that's because, well, we know that one of the properties of metals is that they conduct electricity. And it's also because our nervous system runs on weak electric impulses. So because we're electrical conductors, as we rub our feet against the carpet and electrons move onto our body, those electrons have the ability to move around and distribute themselves evenly throughout our body. Because remember that electrons don't like each other, they repel. So extra electrons on your body are going to distribute themselves in such a way that they minimize their total repulsion. Now, that would not apply to a material that's an insulator, because when you rub an insulator against another object and that insulator picks up electrons, the electrons don't have the ability to move around this insulating material. So the electrons would stay in that area that was rubbed. But we're going to come back to that a bit later. Now, charge cannot be created or destroyed. We've learned in the past that energy can't be created or destroyed. We probably also learned that matter or atoms cannot be created or destroyed. In the same way, charge cannot be created or destroyed. So that's why we say that charge is conserved. So when you rub your feet against the carpet and a negative charge is transferred to you from the carpet, if the carpet has given up 20 electrons that have now moved onto your body, then that carpet will become positively charged by the 20 electrons, and your body will become negatively charged by those 20 electrons. Here's another example where we can demonstrate the conservation of charge. So take two neutral objects. We've got a plastic ruler and we have a cotton cloth. Now, this is obviously not accurate because a plastic ruler is made up of many more than 9 positive charges and negative charges. These materials are made up of millions of atoms. But just for demonstration purposes, the ruler is made up of 9 positive charges and 9 negative charges, making it neutral. And the cotton cloth is made up of 5 positive charges and 5 negative charges, also making it neutral. Note that 9 plus 5 means that the system has a total of 14 positive charges and 14 negative charges. Now, take note that to start with, the objects are neutral, meaning that they have the same number of pluses as minuses. And note that we represent the positive charge with a plus and the negative charge with a minus. And it's just to illustrate the balance of charges. It doesn't indicate the actual location of the protons and the electrons in the material. Now, if the ruler and the cotton cloth are rubbed together, then negative charge would get transferred from the cloth to the ruler. Now, your next question would be, well, how do I know which material transfers the electrons and which material gains the electrons? And that will come to in a moment. But for now, I just want you to note that because electrons have moved from the cotton cloth to the ruler, then the ruler now becomes negatively charged because it has gained electrons. And the cotton cloth is now positively charged because it has lost electrons, so now it has a deficit of electrons. Now also note that if the cotton cloth has lost 3 electrons, then the ruler has gained 3 electrons. And note that the total number of positive charges and the total number of negative charges in my system remains 14. So what that means is that no charge has been created, no charge has been destroyed, it's just moved around within the system. So the ruler is now negatively charged because it has an excess of electrons, and the cloth is positively charged because it has an electron deficit. Again, if you count all the positive and negative charges in the system as a whole, then we're going to find that the total number of protons and electrons hasn't changed before rubbing to after rubbing, and that means that the total charge has been conserved. Charge can never be created or destroyed, but what we do know is that electrons can move around from object to object. So this brings us to the principle of conservation of charge, which simply tells us that in an isolated system means a system where nothing new can enter and nothing can leave the system. The total charge remains constant. This is a nice definition. So if you're asked, what is the principle of conservation of energy? That would mean that in an isolated system, the total energy remains constant. The principle of conservation of mass, in an isolated system, the total mass remains constant. Now, let's come back to this question. When it comes to objects that can get charged, how do we know which objects can be charged, which objects can't be charged, and of the objects that can be charged, which objects gain electrons and which objects lose electrons? So in order to know this, we need to refer to this tribo-electric table over here. And this tribo-electric table was created by scientists, and it lists materials in order from very positive to very negative. Now, these materials that are listed over here are materials that can gain or give up electrons. If we look at the top of the tribo-electric series, we can see that objects or materials at the top of the table tend to become positive, meaning that they give up electrons. And materials further down the tribo-electric series tend to become negative, meaning that they gain electrons. So let's take a look. So the key thing to note is which material is more positive higher up in the table, and which material is more negative lower down in the table. If we rub together glass and hair, which one will become positively charged and which one will become negatively charged? So we need to come to this table, and here's glass and here's hair. Now glass is higher up on the table, so it is going to become positive, whereas hair is lower down in the table, so it is going to become negative. So what does that mean? If the glass becomes positive and the hair becomes negative, it means that electrons are transferred from the glass to the hair. So glass is positive and hair is negative. This means that electrons were transferred from the glass to the hair. Let's take a look at another example. So here we have steel and polyester. So here's polyester in the table, and here's steel in the table. Steel is higher up than polyester, which means that it becomes more positive, whereas the polyester becomes negative. That means that electrons are transferred from the steel to the polyester. So the steel's positive and the polyester is negative, and that means that electrons were transferred from the steel to the polyester. And let's look at another example. Now we've got polyester still, but this time we're rubbing it with silicon. So we're rubbing it now with something that is below it in this tribo-electric series. In the last scenario, where polyester was rubbed with steel, the polyester became negatively charged. But if the polyester is going to be rubbed with silicon, the polyester is further up the table than silicon, so the polyester will actually become positively charged. So polyester is positive and silicon is negative. This means that electrons were transferred from the polyester to the silicon. Now just note that you are not expected to know this table off by heart for tests or exams. You will be given a question that says something along the lines that you've rubbed polyester and silicon together and the silicon has become negatively charged. And you'd be expected to answer questions from there. Let's discuss the force between charges. So when we're talking about these charges, we're talking about static charges, and that is called electrostatic force. What we know is that like charges repel. That means that a negative charge will repel another negative charge, and a positive charge will repel another positive charge. However, a positive charge and a negative charge will attract each other. What we also need to know about this electrostatic force is that it is directly proportional to the strength of the electric field. What I mean by that is that regardless of whether it's an attractive or a repulsive force, if I have a certain charge here and a certain charge here and they attract, but then I make this charge 3 times bigger and I make this charge 3 times bigger, what does that mean for the attractive force? It means that it is stronger. So the electrostatic force is directly proportional to the strength of the electric field. So if I've got something that has a bigger charge, it has a stronger electric field around it. If something has a smaller charge, it has a smaller electric field around it. And a bigger charge with a bigger electric field will mean a stronger electrostatic force. Smaller charges with smaller electric fields will mean that the electrostatic force is weaker. The other relationship is that electrostatic force is inversely proportional to the square of the distance between the charges, and we will see that in a formula shortly. But what that means is that the smaller the distance between the two charges, the larger the force that they exert on each other. So if we come back to this diagram over here, imagine we've got a certain positive charge and a certain negative charge, so there's an attractive force between the two. But if I move them closer to each other, then that attractive force becomes stronger. The same applies here. If I move the two negative charges closer to each other, then their repulsive force becomes greater. An electrostatic force of attraction doesn't just exist between a positively charged and a negatively charged object. It also exists between a charged object and an uncharged object, and that's due to something known as polarization, which we are going to be discussing a little bit later. Now, I already touched on this. What we said is that materials that are conductors are going to allow electrons to move through them relatively freely. Now, because they are conductors, things like metals in the human body, the electrons are able to move through them. However, when it comes to materials that are non-conductors or insulators, the electrons don't have that freedom of movement, so they can't move through the material. So things like plastic, wood, and glass are insulators. And any electrons that end up, excess electrons that end up on one of these materials would not be able to distribute themselves evenly throughout the material. They would be stuck in that position where they were rubbed. So let's say I rub a balloon against my hair, meaning that electrons move from my hair onto the balloon. So now the balloon has an excess of electrons. However, these extra electrons will remain in that rubbed area. They will remain concentrated there. They don't like each other. So if they could move away from each other and distribute each other evenly throughout the material, then they would. But they can't do that because they're on an insulating material. On the other hand, if there is an excess of charge placed on a conducting metallic material, then again, remember the electrons don't like each other, so they're going to repel each other. But in this case, they have the ability to move through the material. So they will spread themselves evenly throughout the material in order to minimize their repulsive forces. This brings us to the end of the first lesson on electrostatics. In the next lesson, we are going to look at charge distribution, specifically on conductors, and we are going to apply some formulas and calculations.